presentation. The topic of my presentation is energy storage optimization for grid reliability. Uh, the goal of this paper is to quantify reliability improvement using batteries or any other storage devices. Um, we consider different cost functions for imbalance minimization and also take into account SOC management. Then for dealing with uncertainty, we propose a myopic controller. Um, So this problem is relevant for large-scale storage owners, which could be private or utility-owned, participating in energy markets in faster time scales. The outline of this presentation is we define reliability using macroscopic supply and demand model. We describe the cost functions that we consider in this work. Then why do we need to regulate SOC? Then we propose myopic control for batteries, which minimizes imbalance and also maintains SOC. Then we describe the key results of two of the case studies, and finally we conclude this work. A well-known definition of power network reliability is system average interruption duration index. So is the average outage duration for each consumer served. It requires information such as the number of consumers which are affected in an outage, and we sum it over a longer time horizon, say 1 year. This definition and this SAIDI terms, in order to calculate this, it requires the information of all the outages happening over say 1 year, and often these information is not available in public domain. So it's very hard to use this definition of SAIDI in real world. So we redefined SAIDI in terms of using the macroscopic supply and demand model. We assume that all the imbalance all the imbalance between supply and demand is equivalent to saying as uh, all the unserved consumers. So we sum up all the imbalances over the time horizon, and these imbalances need to be with respect to the active power which is served. So PG bar is the mean active power over the time horizon, and this definition can be converted into reliability as shown here. Um, Now, this definition lacks what it lacks is that the power network in itself has an ability to withstand fluctuation because of inertia, because of system response. For example, continuous operating frequency ranges are listed for some of the countries here. So what it describes is a lower and an upper bound of frequency between which the system frequency is, then the system is considered to be healthy. So they do not actually try to maintain a very stiff frequency of say a point frequency, but it's normally a band. So if it is inside a band, then the system operator is fine with it. So what it means is if with respect to the active power served, if the fluctuation is within certain lower and upper bound, then the system operator is not going to actively minimize the imbalance up to zero. So what we assume in this work is we have a symmetrical lower and upper boundary, and we want the imbalance to be within that band. So what it means in system, suppose there is a contingency happening in the system, then the frequency recovers because of the primary response of the network and the secondary response. So we need to take into account actively the ability of the system to withstand and correct the system response. So that is taken into account using a term epsilon, which represents that if the system imbalance is within this bound, then the cost, we do not consider any interruption happening in the system. And this is translated into SAIDI definition as shown here. Um, so we are going to use this definition of SAIDI for the rest of the work. So for using batteries as fast response reserves, the cost function has three components. It minimizes the the structure of the cost function, which could be quadratic, linear, and we'll detail that in the slide, in the next slide. And then we have to maximize the reliability or minimize the SID as much as possible. At the same time, batteries should maintain a SOC which is around the target SOC level. So why do we want the batteries to be close to the target SOC? So that it has the ability to either ramp up or ramp down at any time. For example, a battery which is fully charged cannot charge any further, and similarly, if the battery which is fully discharged cannot discharge any further. So both these scenarios are undesirable because we do not know how the imbalances are going to happen in the next or in the subsequent time steps. So the constraints of optimization are related to battery constraints such as ramping and capacity constraint. And there are constraints due to relaxation of bilinear terms, which comes because of the structure of the cost function. We consider three different cost functions. First is linear, in which any amount of imbalance outside zero is linearly penalized based on the magnitude. The second is quadratic. So it makes more practical sense because often imbalances with larger magnitude has much severe effect on the system compared to magnitude smaller magnitude. The third is a linear with a system response cost function, in which if the imbalance of the system is within certain bound, then the cost function is not then the cost function is zero. However, if it exceeds beyond these boundaries, then it has a linear structure. So we can simplify this cost function using bilinear terms and binary variable. These bilinear terms can be convexified using McCormick relaxations. The details of these are listed in the paper. So we use these cost function to solve deterministic convex optimization based algorithms and for solving these cost function. Now we compare these deterministic solution with respect to a myopic algorithm. The myopic algorithm has 9 cases. It takes into account 3 state of charge cases and 3 supply demand cases, imbalance cases. Now, the algorithm looks at where the SOC is. Is it below the lower boundary? Is it within the lower and the upper boundary? Or is it low above the upper boundary? Similarly, it checks the imbalance. Is it lower than the minimum level of permissible imbalance? Is it within the bounds of imbalance? Or is it more than the maximum level of imbalance that the system can sustain? So based on these levels, we have 9 cases, and these 9 cases are used to decide what is the output of the battery should be. And this output of the battery considers the ramping constraint, the charging and discharging efficiency, and the battery capacity limits. I'll give an example. Consider the battery is in state R1, and the imbalance is in U2. So which means that the imbalance is within the bound, but the battery capacity is lower than the lower limit of SOC. So the desired action for the battery is to charge the battery so that it can the SOC level can come within this bound, the lower and the upper bound. Now, since the imbalance is within the permissible levels, the battery will charge in such a way that the new imbalance based on the battery action to charge is within these bounds. The details of the algorithm is listed uh, in the paper. Now we describe some of the results. We performed 2 case studies. The first case study is done for Elia in Belgium, in which we have different size batteries, and we see the marginal effect of these batteries in improving the reliability of the system. And how does system response affect these reliabilities? So what we observe is, as we increase the size of the battery, the marginal increase in reliability is not to the same. So it kind of saturates as you increase the battery size. So for example, here we have different size batteries, and when we compare it with on a log scale, the reliability improvement, we see that as we increase the size of the battery, it kind of saturates. So these different levels are based on different system response that has. For example, 1% system response means the system can sustain 1% active power fluctuation. So the active power, if the active power is say 100 megawatt, it can go from 101 to 99, 99 to 101. The second case study is done for BPA in the US. We consider 1 week of imbalance data for the week for 1 week in May 2019, and we consider a battery capacity of 100 megawatts. So with different cost function, we calculate the reliability, the new reliability with and without the battery. For example, without the battery, the reliability. So we'll just consider one case as an example to show how to read this table. So, for example, if the system response is say 1%, then we have a reliability of 98.9%. And based on these different cost functions and the myopic and control algorithms, we see that the reliability improvement is similar, fairly similar with respect to the deterministic. In this case, it's actually better. So what it means is the deterministic algorithm, the myopic algorithm proposed approximates the deterministic control for batteries, and this keeps improving as the decision making is done faster at faster time scale. For example, these results are performed for a time scale for in which decisions are made in every 1 minute. So, for example, in PGM, where the decisions is by ancillary service participants are taken every 2 seconds, in those cases, the we anticipate the myopic algorithm will perform even better compared to what we have here. So it's a subject for future study in which we analyze the effect of sampling time on the reliability improvement using myopic and deterministic control algorithms. So with this, I would like to conclude my presentation. I presented algorithms for control of batteries using a macroscopic supply and demand model. We show that the system dynamic response due to inertia and governor control impacts the effect of storage in improving grid reliability. For real-time optimization of storage, we present myopic alternates to deterministic storage algorithms requiring full information and show their comparable performance using real data from Elia in Belgium and BPA in the US. We show that storage control algorithms can maintain SOC without significant loss in reliability. Um, Thank you all for attending my talk, and stay safe, all of you. Thank you.